So let's talk about the concept of work. As I said before, I touched on it earlier. We're going to look at it in more detail as it applies to systems that we're interested in. So, as we said before, work is said to be done when force is applied to an object and the object moves a distance, all right? Work is different from heat, right? In that, as I said before, work is caused by a force moving an object through a distance, whereas heat is basically the energy transfer due to a difference between the temperature of the system and surroundings, all right? Now, they're both energy transfers, but the reason why they transfer energy is different. In the case of heat, the transfer of energy is due to temperature differences between the system and surroundings, and in the case of work, the transfer of energy is due to an object being moved a distance by the application of a force, all right? What you're going to see in this chapter is that you have to pay close attention to the signs associated with certain values like work and energy and so on, all right? And it's very important that you know how to interpret what these signs mean. So as stated here, whenever you have a negative sign associated with a quantity of work, what that means basically is that the system is losing energy due to the work being negative. On the other hand, if the work is positive, that means that the system is gaining energy, all right? So the transfer of the energy would be from the surroundings to the system, all right? So it's very important that you relate the sign to the energy changes that is taking place for a particular system. So another statement here is that there's no such thing as negative energy or positive energy. Basically, the sign of the energy change, be it due to work or heat flow, is basically indicating the direction of energy flow, right? So basically, if the energy is flowing into the system, then as far as the system is concerned, the energy change will be positive. If the system is losing energy, if the energy flow is away from the system or out of the system to the surroundings, then the system would be losing energy, all right? So that's what the signs indicate. Okay, so what we're going to do is apply what we have just learned to this hypothetical situation right here. So here we have a gas trapped in this container, and we're going to assume that this plate, which covers the gas in the container, is basically free to move. So there's no friction between the plate and the container, all right? So here we have the gas at an initial volume, and then here we have the gas at a final volume, which is greater than the initial volume, right? So the height of the plate, when you compare the two, the height difference is given by h, right? So let's say we're going from this state to this state where the gas is undergoing expansion. What that means basically is that the gas will be doing work against the surroundings, right? And the change in volume of the gas would be the final volume minus the initial volume. And this is another thing I need to mention here. What you're going to find is that you're going to be determining or using a change in some quantity. And it could be the change in volume, it could be change in other terms. What you need to remember is that when we're talking about the change of anything, we're talking about the final value minus the initial value, all right? So in this case, the change in volume would be the final volume minus the initial volume, all right? So, as I said before, as the gas expands, it is doing work against the surroundings. So therefore, the energy flow would be from the system to the surroundings as the gas expands. And therefore, the value of work will be negative in this case. So the work done on the gas would be minus P times the change in volume, delta V, right? And while I'm at it, I'm not sure if you guys have met this symbol before in your math courses, but whenever you see this triangle, it's actually a Greek letter delta, and it represents change off. So delta V would be change in the volume, all right? So this is the formula that is used to calculate the work done on the gas as it expands or as it contracts. In this case, we're talking about expansion, and in this case, because of the negative sign here, the work done on the gas will be negative, all right? Okay, the last thing I'm going to talk about, actually not the last thing, but let me talk about state functions. Again, another term that you'll meet in this particular chapter. So I'm quite sure you're familiar with from your previous experience, states of matter, right? Solid, liquid, and gases, right? So in actual fact, to be perfectly honest, that's not enough in terms of describing what a state is. The definition of a state is its exact condition at a fixed instant, all right? So state, that term can apply to what you previously learned as the phases, solid, liquid, and gases, but it goes beyond that. So for example, well, before I get into the example, let me talk about this line right here. The state is determined by several factors, including the kinds and amounts of matter present, the structure of this matter at the molecular level, and prevailing values such as pressure and temperature. So all these things can affect the state of a system, all right? And then we'll talk about state function. But before we get to that, let me just give you a few examples of changes of state. Let me get out of this here, and let me go back to my writing tablet here. Let me get rid of this. And let me just give a few simple examples. So let's say you have hydrogen gas, and let's say the pressure of the hydrogen gas that you have is, let's say the pressure is 2.00 atmospheres, right? And let's say that you decided to increase the pressure of the hydrogen gas from 2.00 to 10.00 atmospheres. Then what we have here is a change of state. Because even though they're both in the same gaseous state, by virtue of the fact that the pressure has changed from 2.0 atmospheres to 10.0 atmospheres, we're talking about a change in the state of hydrogen by simply adjusting the pressure. Let me give another example. Let's say you have iron, which is a solid, at, let's say, 30 degrees Celsius, all right? And let's say you decided to heat the iron such that its temperature increases from 30 degrees Celsius to 100 degrees Celsius, right? Again, we have a change in state. Why? Because even though it's in the same solid state, so to speak, the temperature has changed from 30 degrees to 100 degrees. What that basically translates into is different energy states for the actual particles, the atoms of iron that are present, right? And how they behave. So for example, the iron atoms here at 30 degrees will vibrate at a slower speed, so to speak, or frequency compared to the iron atoms at 100 degrees Celsius. So I'm just using these two simple examples to illustrate what we mean by states in the context of thermochemistry. We're basically talking about the condition of a particular system based on, things like temperature, pressure, the amount of matter, and the kinds of matter, and so on, right? So it's very important that you appreciate and understand what we mean by state of systems in this context. Okay, so I was going to get into what we call a state function. A state function is basically a quantitative property that has a value that depends on the current state of the system, and it is not dependent on how the state was reached. In other words, it does not depend on the history of the system, all right? So we're going to learn about different state functions later on, such as enthalpy and others. And in general chemistry too, for those of you who have to do that course, you're going to learn about some other state functions like free energy and entropy, but we won't be doing that in this chapter. Excuse me. Okay, now, the last line here, I'm sorry, is the law of conservation of energy, which is also known as the first law of thermodynamics. And basically what this law says is that in any physical or chemical processes, energy can be exchanged between the system and its surroundings, but no energy can be created or destroyed, all right? And one simple statement that basically summarizes that law is that energy cannot be created or destroyed in such processes. Now, there are a couple of things we can conclude based on this law. One, excuse me, is that the internal energy change of a system is simply the difference in the energy between its final and initial states. In other words, the change in internal energy is equal to the final internal energy value minus the initial internal energy value. Okay. Another conclusion we can arrive at is that if the energy change occurs only as heat and or work, then this is the relationship between the change in internal energy, heat, and work, and it is given by this equation. The change in internal energy represented by delta U is equal to Q, which is the amount of heat change occurring, plus W, which is the amount of work that is done on a system. All right, so basically that's a relationship that can be derived from the first law of thermodynamics. And in some textbooks, in fact, I would say in most textbooks, the first law of thermodynamics is actually expressed according to this equation right here. All right. Now, going back to something we mentioned before, the sign convention, it's very important that you understand and appreciate what the signs mean, especially when it comes to the first law of thermodynamics, right? Whenever you have energy entering a system, that means that the change in energy for the system is positive, and that can be done by one of two ways: by the system absorbing heat, right, from the surroundings, or work being done on the system by the surroundings, all right? And if both of them occur, then definitely the total energy change would be positive, all right? Now, if on the other hand, energy is leaving the system, in other words, the change in internal energy would be negative, then that can be done by one of two ways: either by the heat given off by the system or the work done by the system on the surroundings, all right? So going back to the first statement here, if delta U is negative, right, that means that either Q is negative, right, which is the heat that is absorbed by the system. I'm sorry, if delta U is positive, that's what we mean by heat energy entering the system. If delta U is positive, that means that Q is positive and work done is also positive, all right? On the other hand, if delta U is negative, then that means that Q is negative or the work done on the system is negative, all right? So that's basically how you interpret the signs when it comes to applying the equation for the first law. So let me apply what we have just learned to this example. Now, in this question, you have to read it carefully, especially when it comes to determining what signs you're going to use to represent the different terms. Now, look at how the question is worded here. It says a gas does 135 joules of work while expanding. At the same time, it absorbs 156 joules of heat. So the question is asking, what is the change in internal energy? So what the question is asking for here is delta U. So remember, delta U is equal to Q plus W, right? So the question says, let's deal with the heat part first. It absorbs 156 joules of heat. So if the gas is absorbing 156 joules of heat, that means that Q is positive. So therefore, the value of Q would be plus 156 joules. Whoops. 156 joules, all right? And then, let me put that in parentheses. And then as far as the work is done, work is concerned, the question says that the gas does 135 joules of heat, which means that work is negative. So this would be minus 135 joules, all right? So that's basically how you set this up. So let me do the number crunching here. So 156 minus 135. And according to my calculations, this works out to be equal to 21 and actually plus 21 joules. So basically, the overall change of internal energy for the system, in this case, will be positive 21 joules, all right? So this example underscores the importance of reading the question carefully so that you can determine the correct signs for the numbers that are given in the question, right? Let me just reiterate. When the question says the gas does 135 joules of work, that means that the sign as far as the work is concerned that is done by the gas is minus 135 joules, and it absorbs 156 joules of heat, which means that basically, as far as Q is concerned, that will be positive. And then once you put the numbers in and do your calculation, that will give you the change in internal energy. Okay, we're going to stop here. And the next topic we're going to talk about is heats of reaction. All right? Okay, until next time.